बिस्मिल्लाहिर्रहमानिर्रहीम। रब्बी ज़िदनी इल्मा। ऐ मेरे रब मेरे इल्म में इजाफ़ा फरमा, आमीन। अस्सलाम वालेकुम class, I am your physics teacher Iram. We are discussing chapter number 13, electrostatics. Today we will discuss the topic electrostatic potential or electric potential. After learning this topic, you will be able to define electrostatic potential, understand the concept of higher and lower potential, define potential difference, and solve the numericals by using relative formulas. Let's recall some important points. Every charge creates electric field around it, within which it can attract or repel any other charge. Field is the area around any charge within which it can exert a force on any other charge. Electric field lines are used to show the electric field around any charge. The electric field lines show the electric field intensity by drawing lines. They are for our convenience. Electric field lines originate from positive charge and enter into the negative charge. These lines were introduced by Michael Faraday, and these are imaginary lines around a field charge with an arrowhead indicating the direction of force. These field lines, as I have told you, are directed from positive charge towards negative charge. So electric field is strong where the field lines are close to each other. The area around the charge which is close to the charge have strong electric field, and as the distance from the charge increases, the electric field becomes weaker. So let's start with electrostatic potential, how we can define it. Electric potential at a point in an electric field is equal to the amount of work done in bringing a unit positive charge from infinity to that point. It means we can find out the electric potential of any point in the electric field of any charge. Let's have a positive charge and its field around it. So if we have to bring a positive test charge in the field from any other point, so we have to do some work, because as this positive charge will repel the other positive charge, so we will have to do some work to bring it inside the field. So the potential at any point at inside the electric field will be different from the other points. So we can say that electrostatic potential at any point inside the field will be different, and it will be equal to the amount of work done in bringing a unit positive charge from infinity to that point, the point whose electric potential is required. Its formula is V equals to W by Q, where W is the work done, Q is the test charge which we are bringing inside the field, and V is the electric potential at that point where we have to bring that test charge. What is volt? Electric potential is a scalar quantity. It is just the amount of work. Its SI unit is volt, which is equal to joule per coulomb. As I have told you that the electric potential V is actually W divided by Q. So the unit of W is joule and the unit of charge is coulomb. So joule per coulomb is actually volts, represented by V. It can be defined as, if 1 joule of work is done, here is the 1 joule, against the electric field in bringing 1 coulomb positive charge, the test charge which we are bringing inside the field, if it has a charge of 1 coulomb on it, and we have to take it from infinity to any point in the electric field, then the potential at that point will be 1 volt. We have to define volt as, if 1 joule of work is done against. Why it is against? Because we are taking a positive charge inside the electric field of a positive charge, so we have to do some work against the electric field, as from positive charge the electric field is drawn like this in the outward direction, so we are bringing the charge in, so it is against the field. So we can say that the work done in bringing 1 coulomb positive charge from infinity to a point in electric field, then the potential at that point will be 1 volt. Here is the representation that we are taking a charged particle from infinity to some point. Work done by moving a charged particle from infinity to other point is equal to electric potential. Here one thing you will keep in your mind is that the positive side is called high potential, it has high potential energy, and negative side of anything or of the field is we can say that it is at low potential. So the positive charge will be taken as high potential and negative charge will be taken as low potential. How a charge will move in an electric field? Here you can see that two plates are here. One is having positive charge and second is having negative charge. As I have just told you that the positive charge, we have to take the positively charged side as to be at higher potential and negatively charged side to be at lower potential. So according to the electric field intensity, the electric field lines will be drawn like from positive to the negative. This is the direction of electric field. It is always drawn from positive to negative. Now if we have a positive charge, it will move in the direction of electric field because it will get repelled from the positive side and it is attracted toward the negative side. So it will move in the direction of electric field. But if we take a negative charge inside this electric field, what will happen? It will get repelled from the negative plate and it is moving towards a positive plate. But as its direction is opposite to the electric field line, so we can say that it is moving against the electric field. Here you can see the electric field does work on the particle. We can express the work as a change in electric potential energy. As I have told you that the electric potential at any point inside the electric field is different from the others. So as these charges are moving, so they will move from a point of one potential to a point of another potential, means there will be a difference in the points from which they are moving and towards the other point to which they are moving. They will have different potentials. As you can see, one there is a positive plate and the second is a negative plate. These lines show the electric field. A positive charge is moving from this to this point. First point is this and this is the second point. So we can say that the particle is falling in the direction of electric field. This is the electric field, direction of electric field, and this is the direction of movement of positive charge. So we can say that it is moving in the direction of electric field, and the electric field is doing work on the particle, which can be expressed as its electric potential energy, because it is now moving from one to the other point. It will have different energy within the field. Let's discuss the potential difference. As just I have told you, the electric potential is different at different points. So what should be the definition of potential difference? The energy supplied by a unit charge as it moves from one point to the other in the direction of field is called potential difference between 2 points. Here you can see a charged particle. This is Q. It is first at point A and it gets repelled from the positive plate, means from higher potential it is moving to lower potential towards the negative charge. So let's consider it is moving from point A to point B. As it is moving from higher potential to lower potential, it will release some energy. it will supply some energy. So the energy supplied by a unit charge as it moves from one point to the other in the direction of field, as the unit charge is moving in the direction of field, we can guess that it is a positive charge. So it is the potential. So the energy supplied by that positive charge by moving from higher potential to the lower potential, that is actually potential difference between 2 points. The points near to the uh, higher potential is are they have, what we can say, they have higher potentials, higher electrical potentials, and the points away from the higher potential means to the lower potentials have lower electrical potentials. So the difference between any 2 points through which the charge is moving, let's say in this case from point A to point B, the energy supplied by that charge will be equal to the potential difference between 2 points. For example, if the point A have 5 volts electric potential and point B have 2 volts electric potential, the difference between these two will be 3 volts. The energy supplied by the charge will be equal to potential difference between these 2 points. Here, if a positive charge is transferred against the field direction, energy would have to be supplied to it. We have discussed the case in which a positive charge is moving from higher to lower potential. But what will happen in this case from A to B? But what will happen if we take that positive charge from B to A? In this case, when it is moving from A to B, it is giving out energy. It is supplying the energy because it is moving from higher to lower potential. But what will happen if we take this charge particle from B to A? So as it is positive charge, so it will get repelled from this positive charge rod. So we have to do some work. We have to supply energy to it so that it can move from B to A. And this is the exceptional case, that if a positive charge is transferred against the field, so from its movement we can say that it is moving against the field because it is moving from lower potential to higher potential, but the electric field direction is from higher potential to lower potential, so it is moving against the field. In that case, energy would have to be supplied to it, and that will be equal to potential difference between that 2 points. It is moving from B to A, so that much energy we have to supply to it so that it can move from B to A easily against the field. Here you can compare the gravitational potential with electric potential. Here you can see, I hope you remember that if we take any object at a height from the surface of the earth, its potential energy increases because we know that the potential energy has formula mgh. So greater the height, greater will be the potential energy. It means this is a point of higher potential and this is the point of lower potential, and whenever we dropped this object, it will come back to it. In this case, it will come back towards the surface of earth. In that case, the ball will release the energy. The energy is released by the ball. But if we want to take the ball from lower to the higher potential, we have to give energy to it. We have to throw it. We have to give our muscular energy to the ball so that it can move from this point of lower potential to a point of higher potential. Similarly, in the case of a charged particle, electrical potential energy increases in this way, and as it goes away from the charge, its electrical potential decreases. Same in the case of this uh, example. You can see that we are having a positively charged side and a negative charged side. The electric field lines are drawn like this, and a positive test charge q is here, which is moving in this direction. Suppose it is moving from point A to point B, then what will be the potential energy? In this case it will be W equals to QVAB. Here, because it is supplying the energy, we can say that the energy supplied by the charge is actually QV, where V is the potential difference between the points A and B. So if VA is the electric potential of point A and VB is the electric potential of point B, then this V will be actually VA minus VB, because A is at higher potential, the point A is at higher potential and point B is at lower potential. So it will be E equals to QV. This is actually in this case it is actually the work done by the charge by supplying energy, and it is equals to the product of the amount of charge and the potential difference between these 2 points. Here you can see a formula. E equals to VAB divided by D. V is the electric potential divided by D is the distance between these 2 points, that are A and B. Let's see how this formula is derived here. Here E is the electric field intensity. Electric energy and electric field intensity both have same symbols. Energy both have the same symbols. Capital E. You don't have to get confused between these two. This is the energy. Its formula is QVAB, and this is the electric field intensity. Let's see. How it is here. Here you can see that the formula for electric field intensity is electric potential divided by D. In this case it is written as V divided by D, potential difference divided by distance between these 2 points. As you know that the electric potential V is actually W divided by Q, which can be written as W divided by Q divided by D in this form, and W divided by Q can be written as this, and D on its place W divided by Q. Now W, as W is the work done, it is actually the product of force and distance. So F multiplied by D is here, Q multiplied by D, Q are cancelled, so it is left with F over Q. And we know that this is the formula for electric field intensity, we have discussed in the last lecture. So it is also the formula for electric field intensity here. Electric potential energy for uniform fields. How it can be defined? The more we move a charge from A towards B, the more potential energy it has, as we are taking the charge particle from lower potential to higher potential. So as more we take it towards the higher potential, it will have more potential energy, just like the case of a ball taken away from the surface of earth. The more high it goes, the more potential energy it will have. Same is the case with the discharge particle. It is moving from A towards B. The more it gets closer to the higher potential, the more potential energy it will have. The potential energy will be equal to the work done, as the charged particle is positive and it is moving towards the positive potential. So the work done is equal to the potential energy. As you know that the formula of work is F multiplied by H. H in this case the distance between these 2 points, it can be also be taken as D. F equals to FH. Also the formula for electric field intensity is F over Q. Putting the value of F from this case, it is QE. F will be equal to QE, and putting in this formula for W, W will be equal to F is QE and H on its place. W equals to QEH, where W is actually the potential energy. So we can say that potential energy is QEH. Same is the case for potential energy, gravitational potential energy, MGH. Increases with the height, increases with the distance between the 2 points. Here you can see that how potential energy has this formula. As we know that, as we have just discussed, that the potential energy between 2 points is actually the product of Q and the potential difference between these 2 points, where the V is actually W divided by Q. The potential difference is work done divided by Q. So here potential energy is actually the work done, and work done is FH, force multiplied by distance. So the we can say that the work done is in the form of potential energy. Also we know that the electric field is F divided by Q. Getting the value of F as QE, putting in this equation, potential energy will be QEH. Don't get confused in these formulas. These are just for your information. An important term you will see in this topic is Faraday's cage. What are Faraday's cages? A Faraday cage or Faraday shield is an enclosure used to block electromagnetic fields. A Faraday shield may be formed by a continuous covering of conductive material, or in the case of a Faraday cage, by a mesh of such materials. Faraday cages are named after scientist Michael Faraday, who invented them in 1836. Or we can say that as a Faraday cage distributes the charge or radiation around the cage's exterior, it cancels out electrical charges or radiation within the cage's interior. In short, a Faraday cage is a hollow conductor in which the charge remains on the external surface of the cage. These are actually the cages which are used for shielding out the external electric fields or electrical charges. The person or the instrument or anything present within the vicinity of that cage will be safe from the strong electric fields that exist outside the cages. How is that possible? Let's discuss. Here is the Faraday's cage, that how it is constructed. As I have told you that it is a hollow metal conductor, means inside is hollow and a metal is used as a cage. A metal is used to made the cage. As metal have free electrons, but as a whole it is neutral. The positive charges are equal to the negative charges. In the first case you can see this is a metal wall which is having electrons and protons in the same number. Faraday cage in the absence of an electric field. But when an external electric field is applied, you can see positive and negative charge, and that these field lines are from positive to negative charge. The charged particles in the wall of Faraday cage respond to an applied electric field. Here you can see the external electric field is applied. In the third figure, you can see the response of the charges present in the metal, how they respond. As this chapter from the start we have discussed about the electrostatic induction, that whenever a positively charged rod is brought near a neutral thing, the opposite charges will be attracted towards that end, and the opposite charges will be, the same charges will be repelled. As we are seeing that positive charges are here, the electric field is from positive to negative. So what will happen, all the negative charges will be attracted to these positive charges and they will gather on this side. You can see all the electrons are coming here, and this side is left with only positive charges. So what will happen, this charge, this side gets cancelled with the effect of these electrons, because the the electric field originates from positive charge and ends on the negative charge. These electric field lines will stop the external electric field, and on this side, as the positive charges are here, they are having their own electric fields as well, which are like this radially outwards, which are drawn radially outwards. So what is present inside? Nothing is there. No charge is present inside the field. So we can say that electric fields generated inside the wall cancel out the applied field, neutralizing the interior of the cage. The interior of the cage is neutralized. That's why anything present inside the cage will be safe from the outer electric fields. Here is the case that how the exposure of an electric field is with the metal cage. When an electric field is applied, the charged particles within the conductive wall move. In this example, electrons move to the left, giving this part of cage a negative charge, while the right hand side will become a positive charge. That's why all the electric field lines on this side will be cancelled, leaving inner side with no charge. Here are the examples of Faraday's cage in our daily life. You can see as the bodies of aeroplane are made up of conducting materials. They have to travel through the lightning as well, but the passengers inside the aeroplanes are safe because the body of the aeroplane acts as Faraday cages. Same is the case with the cars. You are safe inside the car whenever there is a lightning bolt, and the electric elevators in the tall buildings also act as Faraday cages to prevent the outer electric fields to harm the inner materials. That was all about our today's topic. If you have any question, you are welcome to ask anything anytime. It's your homework. After watching the video and reading the topic from book, you have to answer the following questions. In what direction will a positively charged particle move in an electric field? If there is an electric field of a positive charge and you have to bring a positive charge inside that field, in what direction it will move? And what is the unit of potential difference? You also have to do the practice of these figures mentioned here on your rough copies because they are very important. You have to draw with the questions as well. Thank you and Allah Hafiz.